Hello everyone. So whatever greeting is there in your times, and right now it's 5 a.m. So good morning and thanks a lot for taking time out of our lives. So today we're here to attend a webinar on Introduction to Computing, Quantum Computing Programming with Python Qiskit with Sara. So hello. So my name is Qiskit. I am doing biotechnology engineering. I'm a student. So yeah, that's about me. Let's go ahead. So our mission is to, so you can see from both mission from Women Who Code, that is inspiring women to excel in technology careers. So yeah, that's about it. So I hope it's it's there to sink in, because you don't see that much around, and it's really great that all of us can come together at different time zones and attend an event just because someone is there. So thanks a lot for that again. And our vision. So yeah. So, the Women Who Code vision is to create a world where, women are representatives of technical executives, founders, VCs, board members, and software engineers. And, there are no barriers. There's just execution and self-expression. So, yeah, looking forward to it. So, that is our target. Engineers with 2 or more years of experience looking for support, resources to strengthen their influence and level up in their careers. So for more information, you can check out the Women Who Code website, and it'll be great. So you can find resources, there are job applications there, it's everything there. So it's one place for all women to empower each other. Women Who Code has a code of conduct. So yeah, so Women Who Code is an inclusive community dedicated to providing an empowering experience for everyone who participates in or supports our community, regardless of gender, gender identity and expression, sexual orientation, ability, physical appearances, body size, race, ethnicity, age, religion, socioeconomic status, caste, creed, political affiliation, or preferred programming languages. Our events are inherited to inspire, to excel in technology careers, and everyone who is there for this purpose is welcome. We do not tolerate harassment of members in any form. Our code of conduct applies to all Women Who Code events and online communities. So you can read more about this on our website, or you can even report about it on womenwhocode.com/code of conduct. So yeah, feel free. Anyway, so what happens. So our speaker today is Sara. She is a PhD researcher, and yeah, so Sara she's originally from Egypt, and she did her undergrad in the Faculty of Engineering from Alexandria University, where she got her bachelor's degree in electronics and communications. So that's great, and that's not over yet. And after that, she worked for 6 months as an Android application developer. Before that, she traveled to Tokyo, Japan to pursue her postgrad studies. And she got her master's degrees in computer and communication engineering from Tokyo Institute of Technology in 2018. That's great, Sara. And then after she finished her master's, she took a year off to do her research, to learn about quantum mechanics and quantum physics. During this year, she worked as a part-time lecturer at Tokyo Coding Club. And currently she is a PhD researcher in Keio IBM Quantum Computing Lab. So that's a lot of experience. That's so inspiring. Thanks a lot, Sara, for doing this today. And let's get started.
Okay, thank you for the nice introduction.
Yeah, over to you.
Okay, now I need you to stop sharing so I can start.
Yeah.
Hello, everyone. Good morning, or good afternoon, or good evening. Depends on where you guys are joining us from. My name is Sara, as been introduced, and today we're going to talk about quantum computing, Hopefully it will be light and nice introduction for everyone who doesn't know anything about quantum computing. And if you know a little bit, maybe I will add some information, or it will be interesting to kind of just refresh your information. So before I start, the notebook that I'm using today is on the Woman Who Code repository. So if you go to the Woman Who Code repository and go to the Woman Who Code Python, then you'll find it here in the README. And if you click on it, you will just get to my repository, and you can see my the notebook. You can download it and follow along with me if you want to. I think they shared it on the chat. Yes. So it's on the chat. Once if you go to that link, you can just download it and you can follow through with me. And if you have any problems, just let me know. Especially in installing Qiskit. It used to be a hassle when I first started using it 2 years ago, but it got very much better now. Okay, so let's get started. So let me minimize this because I do not like looking at myself while talking. So this picture actually represents what a quantum computer looks like, and it's very famous what it looks like. It looks like a chandelier thing, like this. And actually, the truth is that the quantum computing part of all this chandelier is this little part down there. All this top part is actually a refrigerator. That is, we use to kind of keep the temperature of the quantum computer at bay so we can actually use it. Otherwise, it will overheat. So actually, the quantum computer is this little golden part here. But other than that, this is actually the refrigerator and not the computer itself. Okay, so they talked about me. So currently, I'm working as a researcher in the Aqua Guggenheim University. So if you want to read more about me or about my work, you can visit my website. Or if you want to read more about my research group, which is Aqua, you can also visit our website and get to know the other people who's working on the quantum stuff. Okay, so what is quantum computer? Let's start with that. I don't know if anyone knows what quantum computing is. And one more thing before I start, like I want to keep this workshop interaction. I want some people to ask questions and like raise your hand. I guess you can raise your hand in Zoom if you have a question, and you feel free to stop me at any time because you know it all builds on each other. So if you feel like something is not very clear, you can just understand me right. You can just ask me a question right away. Okay. So quantum computing, maybe a lot of people has heard of it. Maybe it's that cool thing, that mysterious that no one really understands, which is true. No one fully understands 100% of quantum computers, especially the quantum physics and mechanics part of it. Maybe the programming is a bit easier, but quantum computing in general is a computing technique or a computing approach that takes advantage of quantum mechanics phenomenon, just like superposition and entanglement. And actually, superposition and entanglement as like the only thing that differentiate classical computers from quantum computers. So let's talk about the 3 pillars of quantum computers, which are superposition, entanglement, and qubits. We'll start with the first one, which you need to know is superposition. Superposition, in my opinion, is like the most famous quantum concept out there. Maybe not by its name, superposition, but everyone have heard of Schrodinger's cat, one way or the other. It's a cat that is locked in a box with a poison. And you don't know if the cat is dead or alive because it is locked in the box. So we don't know if it ate the poison, if it's dead, or if it's still alive. So we can say that the cat is in a superposition state of being both dead and alive. And we can say that just because we don't know if the cat is dead and alive, right? So until we actually open the box and see whether or not it's dead or alive, we actually have no way to knowing if it's dead or alive. So that's pretty much what superposition is. Superposition is this uncertainty thing. Because we don't know if something is at one state or the other, we assume that it's at a 50-50 chance, okay, of being in either states. So the cat is in a 50-50 chance of being dead or alive. That is only until I open the box, and then it becomes either 100% dead or 100% alive. It cannot be actually both in the same time. So that is superposition. I know it's a little bit confusing. How can one thing be in two states at the same time? But the truth is, it is not. It's actually because I don't know what state it is in. I assume it's in two states at the same time. But the truth is, once I measure it, or once I read it, and once I look at it, it's only going to be in one state. Okay, so now we're going to talk about qubits. And this is a picture of actually 4 qubits. 1, 2, 3. So the squiggly things here are qubits. Are they connected together? This is from one of the IBM old machines. Like you can see a multiple group of qubits. So a qubit is the core of quantum computing. Just like in classical computing, we measure everything in bits, kilobits or megabits. In quantum computing, we measure everything in terms of qubits. Okay, so qubits represent like the ability of quantum computer to actually do any kind of computations. And a qubit, unlike an actual classical bit, so classical bits are kind of an imaginary term, right? So a classical bit can represent either the passage or not passage of electricity in a wire, right? If there's electricity, then it's 1. If there is no electricity, then it's 0. But the actual classical bit does not exist. It's an imaginary thing. However, quantum bits or qubits actually exist, or you actually build them. Like this is here, as I told you, this is a qubit, and this is a qubit, and this is a qubit. So they're actually kind of like a hardware thing, or like something that exists in real life, that it's not imaginary. Okay, so in programming or in quantum computer, we often use something called the direct style or the kit notation to represent qubits, to kind of differentiate them from classical bits. So if we're using classical bits, we say 0 and 1 like that, just normal numbers, 0 and 1. But if we're using quantum stuff, we say ket 0 or ket 1. And the way we read them is to say that 1 state or 0 state. So we call them as states. Okay. So that is qubits. And qubits are difficult to manufacture. There are so many kinds of qubits out there. There's a lot of companies trying to kind of race to reach quantum supremacy. Google claimed that they did sometime last year, which wasn't completely true. In Google, they're using a methodology called ion trap to create their qubits, where in IBM, they're using superconducting materials to create qubits. So the difference is like in the same materials that they're used to create the qubit itself, like the chip that has the qubits. Because just like I said, qubits are actually there, like you embed them on the chip. It's not like classical bits, which are imaginary. Okay. Of course, because it depends on the materials that it's used to create it. Like, is it a superconducting qubit or is it an ion trap qubit? There's spin qubits, there's photonic qubits. There's so many kinds of approaches that one can take to actually create a qubit. Of course, none of the qubits that exist now are good enough to actually compute a real-life application. You can compute a simpler version of a real-life application, but to compute a real-life application, we need millions of qubits, which are not there yet. Also, the qubits now are very faulty, which means they have a very high noise ratio. So computing using it does not always lead to, accurate results, or the results that you would think that should be computed. Okay. Now let's talk about the most confusing term of quantum computing. Well, in my opinion, I think in everyone else's opinion, entanglement is like the confusion of it all. So what is entanglement? I want you to think of entanglement as a relationship between two qubits. The most famous qubit, or the one that is easier to explain entanglement using, is a photon spin or an electron spin. So, when we have an atom, there is like a bunch of photons and electrons like going around the nucleus. Now, if I have 2 electrons, one spinning, these electrons actually kind of like the Earth and the Sun. They spin around the nucleus. They also spin around themselves, so around their own axis. So what we see here, if there's 2 entangled qubits or entangled electrons, that means that the direction they spin around themselves is going to be opposite. It has to. Why? Because entanglement, it's kind of like, as I said, think of it as a relationship. They have to complete each other. Okay. Here I had like, if I assume that I have like two direction of the spin, like let's say up and down. If I say up is the blue one and down is the green one. If they're not entangled, if I have two electrons that are not entangled, they can be at any combination, right? The probability here. They can be either both, they can be spinning in the same direction, they can be spinning in opposite direction, like whatever, opposite up, down, or down, up, or they can both be down. So they both can be up, down, up, or down. But if they're entangled, they can only be opposite to each other. They can never have the same direction. Now, luckily, when we do write code for quantum computing, we do not need to deal with entanglement directly, because entanglement is done on a hardware level, if you thought about it. So actually, like for example, if we run stuff on the IBM machines, the way they do create the qubits, they make it entangled somehow. Okay, one of the way to make it entangled is like if I'm using electrons, usually they use like laser electrons, and usually they embed one laser beam and take two electrons from the same laser beam. Because they were embedded from the same source at the same time, they are entangled. There are other complex ways to make two things entangled, two qubits entangled, but we're not going to get into that right now because that's not our point. We want to program a quantum computer, not to make them entangled. So when we program stuff, we do not have to worry about entanglement at all. You just need to worry about qubits and superposition. But just know that mostly when we create superposition states, they usually are entangled. Just something that you need to know in the background, because it's what makes the magic happens, in a sense. The magic of quantum computing happens. Okay, so this has been like a light introduction about the three pillars of quantum computing. If you feel like you need to know more about it, I can send you resources. You can contact me on like the Woman Who Code Python chapter Slack channel, and I can help you out if you need more detailed information. But for now, let's get into coding. So if everyone downloaded their notebook, and I hope you guys do, because I would like to help you out if you have problems installing Qiskit, which I hope you don't, but like if you need help, if you download it, like if you just run like a pip install Qiskit, and because Qiskit has stuff that depends on Matplotlib, or to draw some stuff, we're going to use Matplotlib. So these are the two libraries that we're going to need. So if you go ahead and install this, it'll be great. You can install it from the command line, of course, or from here within the notebook. I'm just going to run this cell here so I can start with you, so everything will work. Usually Qiskit takes a little bit of time to actually get imported because it's a very heavy library. So let's talk about Qiskit here for a while. So I'm actually wearing the Qiskit hat. So Qiskit is a library, and it's an open source library. You can access all the code of Qiskit if you want on GitHub. And it's developed by IBM. And the coolest thing about Qiskit is it gives you the ability to actually run stuff on the actual quantum computing, like the IBM devices, which I think is pretty awesome. There are other options if you want to program a quantum computing, and we can just talk about them very quickly here. There's actually three options. And I want you to think about them kind of like the way we think about classical programming language. There are like low-level languages, medium-level languages, and high-level languages, right? So same exists for quantum computer. There are low-level languages, which Qiskit, of course, is not one of them, where you can deal with the, let's say, the hardware of the quantum, and it's called the pulse programming languages. Actually, Qiskit do provide a little bit of functionality on that, and pulse means electrical pulses. So you communicate with the qubits using electrical pulses. Of course, to do that, you kind of need to be a little bit more advanced in using quantum computing and what is quantum technology is, because you need to fully understand the mechanics and physics behind it. luckily, there are other options you can use if you want to program a quantum computing, which is Qiskit, one of them. So Qiskit is one of the, let's say, classical-based quantum programming, let's say, library. So it depends on a classical computer language, which is Python, right? So Python is a classical programming language, but Qiskit uses Python as a kind of like a medium to program quantum computer in a way that is easier for people who's already been programming to use. So you do not need to learn a lot. You already know Python, hopefully. You already know Python, so you can just learn the little bits and pieces of quantum mechanics that you need to build an algorithm. So that saves up a lot of time than if you actually want to use a low-level language. Another option is there are programming languages that is specifically for quantum computing. Now, I have used them before. I do not recommend them for someone who's starting, because for now, they do not have the ability to actually run your algorithm. Plus, they have a very funky syntax. They try to be as close to Python and C++ to possible to make the transition easier, but they still have stuff that you need to be very familiar with the math and the quantum physics behind it in order to understand. So for me, if you're starting to learn quantum computing, I think Qiskit is a great place to start. There are other Python libraries for quantum computing. There is a, let me think about it. There is, I think, I have here more stuff that I can show you about the existing one. So let me see. So yeah, here I have here a folder of all the existing quantum software tools that you can use. If you want this document, I can share it with you. So Qiskit is the most famous one. There's Qtip, which is also based on Python that you can use. And there's also Cirq. So Qtip is built by some researchers, and Cirq is actually built by Google. Well, not officially by Google. It's not an official Google product, but it is built by Google. There's also Byquil, which is another library that you can that Rigetti use, and Rigetti is another company that's joining the race for quantum computing. And of course, for people who are not Python people, don't worry, you're not left behind. There are stuff built on JavaScript, like Quark here or QJS, and there are stuff built on C++ and on Java. I don't think I have anything built on Java here, but there are libraries built on Java. So there are quantum libraries built on most famous classical programming languages, but since Qiskit is the one that actually gives you the ability to run on an actual quantum computer, I feel like that's why it's the most popular. Also because the community of it is very active. So Qiskit have a Slack channel, and if you have any problem with Qiskit or need any help, you can just reach out to the people who build it, and they're actually very responsive and very helpful. So that's a little bit on why I like Qiskit, or why do I recommend people to start with Qiskit. Okay. So here, this piece of code, like this from Qiskit, import quantum register, classical register, quantum circuit, error, and execute are the basic things you're gonna need to actually build a quantum circuit and run it. And we're first gonna run it on simulator. We can run it on a real device. I'll show you how to do that. And we can run it on, we can actually build the circuit on a quantum circuit simulator first, which is also we're gonna do. So we're gonna do a lot of things today. Okay, so here, there's two kind of simulators that IBM provides. As I just told you, the actual devices, although you can run on them, not all of them, but you can run on them, they're still faulty and they have a lot of error rate, okay? So there are simulators that IBM provided in this Qiskit, so you can actually see how will your algorithm perform on a perfect quantum computer, which does not exist yet, but you can actually do it. And that's what we do. We actually run it on simulators first, before we run it on real machines, so we'll have a reference. Because if you run it on the machine, crazy thing will happen. And we'll see that later. Okay, so this is our just two kind of simulator. The state vector simulator, we're not going to use today, but it just shows you how the state it is in terms of qubits. The quasi simulator will show you give you back like a histogram object, so you can actually see it visually, which is why I like the quasi simulator better than the state vector. I'm more of a visual person. So to create a quantum circuit, a quantum circuit contains of registers and gates. A register just tells you how many quantum qubits you're going to need and how many classical bits you're going to need. And how many you'll need depends on what you're trying to do. But here is the thing, not all circuits have to have both. I mean, technically all of them has to have quantum registers because you're building a quantum circuit, but not all of them has to have a classical register. We use classical registers to measure the quantum registers. So to store their value, pretty much, because so far quantum qubits does not have a memory, which means it cannot store its own value for like a long time. It will actually fade away. However, if we put them on a classical bit, then we can actually do something with them, like read them or block them or do something with them. So here, this is for our example. We're going to talk about quantum gates now. So I just put 2 classical bits and 2 quantum bits. The reason they are the same is because I need 2 classical bits to measure 2 quantum bits, 1 for 1. And then I created a quantum circuit object that has this quantum register, and that's classical register. Okay. I hope so far there is no problems. If there is, please let me know. Please just shut me up and say, Sarah, shut up, and answer the questions. Okay. I hope there is no questions because I cannot see anything on the chat. I have it there, but there's nothing. Okay. So let's do the quantum gates. I'm not going to talk about all the quantum gates. I hope you guys are familiar with classical gates. I do not know how many of you have like very technical background, classically speaking, but quantum gates are kind of similar. They are kind of like the quantum equivalent of classical gates, like, you know, the AND gate or the OR gate or a buffer. I do not know if you guys know these terms, but I hope you do. If you don't, do not worry about it. So quantum gates are gates that provide a similar, like a functionality that you can do something with the qubits. I like to hint something out. Like when I first started quantum, I felt like the way the way we program quantum computers are the way that the classical computer used to be programmed back in the 80s, but like in a nice syntax, not assembly language. Actually, just using Python to do gates. Instead of like the old people in classical computer, they use assembly language to use gates. So that's an up, but that just tells you how we're like quantum computer is still in an advancing field. It is not well developed yet, which actually means there are so many options to join the quantum field and be researchers and build quantum programming languages if you're interested. Okay. So today I'm going to talk about, I think 4 gates, which are very good to get you started with quantum computing. Of course, maybe we'll do more webinars like on advanced quantum topic like Shor's algorithms or Grover's algorithms or like quantum search in general. And then we'll talk about more gates and more complex terms. But for now, let's just start simple and talk about 4 gates. First one, we're going to talk about the identity gate. And this is like a buffer in classical computer. And the identity gate does not do anything. You might wonder, why would I build a gate that doesn't do anything? Just like in classical, a buffer is important just to make sure that, let's say, we can use it to kind of waste time in a sense that I want the circuit to do nothing. And because quantum computing, like you can't say nothing, like you can't say pause and do nothing like sleep like classical computer. So you just put a gate that does nothing. So it kind of takes a little bit of time, or just to make sure that a qubit is actually an actual value. So that's what the identity operator does. It does nothing. Okay, how do I add an identity gate to the circuit? So you already made a circuit and it's called Okay, that's short for quantum circuit. So to add something to a quantum circuit, you say QC, or the name of the quantum circuit object, dot ident, which is short for identity. And then you put here, what qubit do you want it to apply to? So the identity gate is a 1 qubit gate, which means it operates on just 1 qubit. So you have to give it 1 qubit. Remember here, we did our circuit, we made 2 qubits in the circuit. So this register has 2 qubits. So I have here, when I use this identity, I have to tell it which qubit do I want it to operate on. And here, this is a cool drawing thing. So if I run this, okay, ignore the warning. Obviously, I need to update something. I'll see that here it drew me the circuit, okay, and I have the identity gate, which is I on the qubit 0. I hope that so far is good. Webinars are weird because you cannot see people or like hear them or like see them nod that they understand. So you have to assume that they understand. Okay, so if I keep adding stuff to the circuit, it's gonna be showed up as this blocks with like some letter on it, and the letter usually like represent what kind of gate it is. So if I change this and make it to 1 and run it again, you're gonna see something interesting happen. Like you're gonna see now that the identity is on both 0 and 1. And you might wonder, why is it on both? Here is the thing. Here is the thing. Quantum circuit, like every time I add stuff to it, it's just gonna embed stuff to it. Kind of like think of it as a list in Python, and every time I add a gate, it embeds it to the end. It doesn't create the circuit all over again every time I add stuff. So if I want it to be clean, I just need to define this quantum circuit object every time I use it. But usually we just define it in the beginning and then build a circuit, just keep adding gates to it. So here now I have this identity gate on both qubit 0 and qubit 1. Okay, so this is the identity gate. It does nothing, but it is very useful in big quantum algorithms. Okay, let's talk about the second gate, which actually does something. We're going to talk about the NOT gate. The NOT gate flips the state. So if it gets a 0, it gives me a 1. If it gets a 1, it outputs a 0. So it flips the state of a qubit. And the way we add it, we say the QC, or the quantum circuit, and we say X. X is the NOT gate, and we give it also the qubit to operate on. Again, the NOT gate is a 1 qubit gate, so it needs 1 qubit. So if I run this now, you'll see that I have the 2 identity gates from before, and now I have the X gate. Now we can talk about this wave function, or the vector. See here, see those 2 lines here? These represent the states. So actually, I do not know why it's being printed twice. It actually should be just 1. I think I was messed up a little bit in the wave function, because it's actually a custom function. It's not in Qiskit. However, see here, like just focus on this one. It says here, this here is the probability of measuring this state, which is 1, 0. Okay, so here it says if I measured, or if I just executed this circuit, I should get with 100% like confidence the state 1, 0, which is like 1 here and 0 here. Why? Because this was 0. So all qubits start from 0 by default. So the default is 0. If you want it to be 1, you have to do an X gate or a NOT gate. Okay, we call it X gate because the symbol of it is X, so it makes it more, I do not know, persistent or consistent. So here I have like 2 identity gate and an X gate, and that gives me 1, 0. Okay, hope everyone is good with the X gate. Let's go to the control NOT gate. So far we've been working with 1 qubit gate, which means a gate that takes 1 qubit. The C NOT gate is a 2 qubit gate, which means it takes 2 qubits. One as a control and the other one as the target. Okay, so what does it do? Pretty much it's the X gate, but it has a control. If the control is 1, then it's going to be normal X gate. If the control is 0, it's going to be like an identity gate. It's not going to do anything. Okay? So here, if I apply this, now remember, now I have the 0 here. I have it as 1, right, from before, because I just make it here I just applied an X gate and made it a 0. and the 1 is still 0. Okay, the qubit 1, which is like this one here, it's still 0. Now, if I applied control gate, which is again I use the circuit object, and I say CX as in control X, and the first one is the control qubit, and the second one is the target qubit. So I'm saying use qubit 0 to control qubit 1. Since qubit 0 is 1, that should give me 1, 1. So it gave me 1, 1 because the first one was 1. Oh my God, that's a lot of 1 in one sentence. Because qubit 0 was 1 and qubit 1 was 0. So it flipped it and it became 1. Does that make sense? I hope it does. If I did not apply this X gate here, then I will still be in 0, 0, and nothing will change. Because then qubit 0 will be 0, and then it will not flip qubit 1. So the control NOT gate is a 2-qubit gate, and it just flips the object, it flips the target qubit if the control qubit is 1. Okay, now let's talk about the last and most important and magical gate in the quantum realm, the Hadamard gate. So we just so far, I mean, I do not know if any of you have thought that, but so far you should have thought like, hey, so far there's nothing different than classical bits. So these all these kind of gates exist in classical computers. So where does the quantum part comes in? Here is where it comes in, the Hadamard gate. So far we have been doing things classically. We have some qubits, we have been flipping them and doing some not very impressive things with them. The Hadamard gate is the magic gate, and it is the gate that creates the superposition. Percent between state 0 and 1, despite of the initial state. So if I apply Hadamard gate on a 1, I will still get a superposition, and if I apply it to a 0, I'll still get a superposition, and it's 50-50. The difference is, you do not need to know what's the difference between applying 0 and 1. Just know that in either cases, it will create a superposition between 0 and 1. Now, to make it easy to understand, I'm going to go and run this again. So I will start clean with my circuit, and I won't have all this many gates that we just play with. And I'm going to apply the Hadamard gate. Let's apply it on 0, not just 1. And see here, things started to get different. So far, I've been getting like one thing, right? Like one state with 100% accuracy. But now, no, now I have 2 states. Now notice, I told you that the Hadamard gate creates a superposition between, on any like qubit you apply to. Here I applied it to 0, which is the first one. That's why if you notice, you see that the first one here's 0 and here's 1. That's the superposition, and also this is the superposition. We'll talk a little about the 0.707. But if you see here, the second qubit is unchanged. It's 0 in both cases. But here, I just created a superposition in 2 entangled states. Now let's talk about this 0.0707. See here in the thing that keeps moving fast, you have the Hadamard gate, and then when it gets 0, it becomes like 1 over square root of 2, 0 plus 1. Now, this is the amplitude. And the square, like if I say this is going to be like half 0 and half 1, which is 50-50. Okay, so 1 over square root of 2 is like the 0.707 that we see here. And here it says like 0.07 for the zeros and for the 1. Now, let me do something. I'll just copy that line and put it there so we can try different things and make a new circuit every time for things to be clear. Now, let me do an X gate first. Let's see what happens if I put a Hadamard on a 1 instead of a 0. So now I put it on a 0, right? Because the default is 0, and it gives me like this 0.70700 and like the 0.7010. What if I had an X gate before? So let me put an X gate on 0 before I apply the Hadamard to it and see what happens. How does the circuit change? See the difference? The only difference here is going to be this minus sign. Other than that, it's going to be exactly the same number in the same state, but they're going to be in a different direction. We do not have to worry about directions now, but just know that when we apply it to a 1, it kind of make it to rotate with a specific angle, technically 180 degrees. Okay. Now, if I apply the Hadamard to the second qubit, which is qubit 1, you're going to see that now I have 4 gates. Sorry, 4 states. I have the 0, 0, the 1, 0, the 0, 1, and the 1, 1. And that actually is called the full superposition, or the Hilbert space. The Hilbert space is the full superposition of whatever number of states I have. So here I have 2 qubits, which means my Hilbert space size is going to be 2 to the power 2. So 2 is always constant because it's binary. Technically, it has just 0 and 1. And the power is how many qubits do you have. So 2 to the power 2 is 4, which means the Hilbert space size for 2 qubits is 4. If I have 4 qubits, then it will be 2 to the power 4, which is 16 states. We can actually try that later and see how many states there is. So let's talk about the quantum bases, or the entangled states. So see here, when we did not apply this, can you hear me now? Okay, I'm sorry, I do not know what happened. Okay, so I was saying that we have the quantum states, or the quantum bases. If I apply a Hadamard on a 0, I get something called the plus state. And if I applied it to a 1, I get, so this here should be 1. I think I had a mistake here in this image. This here should be H1. Okay, so if I apply the Hadamard on 1, I get something called the minus state, which are those 2 states, which is also the ones that comes up here in this chart. Okay. Okay, that was a lot of quantum talk, but I hope that the gates are okay with you, and that especially the Hadamard gate. So the Hadamard gate creates superposition. Okay. Okay. So let's talk about quantum circuit simulators, which is like the step before we actually write the code to build the circuit. Usually, to test, when we have an idea about a circuit, or we want to like implement an algorithm. If the audio went off again. Can you guys still hear me? Okay, because for some reason, when like Zoom does not say talking Sarah anymore, I do not know why. Anyway, so quantum circuit simulators are a way for you to build a circuit without needing any code, which I think it's pretty awesome. There are so many quantum circuit simulators out there. My favorite is the IBM Quantum Experience. So if you go write IBM Quantum Experience in Google, you might need to create an account to get to this page here. But as I said, IBM actually have like free devices that anyone can use. I have here more devices since I work with IBM, but it has free devices. Once you go to the IBM Quantum Experience and creates an account, you will have something like this, maybe with not so many experiments and results because you want it will be new, but you'll have some devices that you can try things on. I think for the public, I think there's 5 devices that everyone can use. And if you have like if you work with IBM, or like you're in academic field working with IBM, they usually give you more access to more devices. So these are here the devices that already exist. And by devices, I mean actual quantum computers that IBM built and people can use. But I'm gonna go here to the circuit composer, which is the quantum circuit simulator. Okay, and here it tells you, hey, we have new stuff. So it looks like that. It did not used to look like that, I guess, last week. I think they made an update. Doesn't matter. So here you have a bunch of qubits. You can add some or delete some. And you have here C3. It just says that here you have like 3 classical bits because you have a bunch of qubits. And you can just drag and drop the gate. So this is the Hadamard gate. If I dragged it and dropped it there, you're gonna see here down, like here, it says, hey, now you have like a, let me like, if I delete this and this and I have only 1 qubit and I create a superposition, it's gonna say me it's 0 and 1. This Q sphere is another way of represented quantum states. We're not gonna talk about that today. We can talk about that later. It's a bit more advanced. But if we look here, it says here you have a state 0 with probability 50% and state 1 with probability 50%. Okay, if you want to throw it away, like if you just like drag it and like, I think just put it here or like put X on it, it disappears. And then it says it's a 0 state. You can apply the X gate, which is this one here. This is the X gate, and then it will become 1. As you can see here, 1. You can apply the X gate and then the Hadamard gate, and then you will have again 0 and 1. But we said that the direction will be different. Like, I mean, if you notice here, this is 1 here became red because of the direction of the angle that I just mentioned. But other than that, it's actually going to give you the same thing, which is a superposition, a 50-50 between 0 and 1. There's a bunch of other gates. You do not have to talk about them all, of course. So here, if I just removed this one and I added like the control NOT gate, you'll see that my result is going to be 1, 1 because this was 0, but then I flipped it, it became 1. And now the control is 1, so I'm going to flip this to 1. So it becomes 1, 1. I hope that makes sense. There are different quantum circuit simulators out there. I can share it with you. Again, I can share all the links because there are so many resources you can start with. I can share them all after the webinar. But for now, because of time, let's move on. So let's build our first quantum circuit. It's going to be a very simple circuit, but let's start with it. So here I'm telling you how do we read like a kit notation state. So the 0 is like the first one on the left here. So we read it from the left to right, 0, 1, 2, 3. Okay, this is just, I'm pretty sure it's like, so here, unfortunately, in this picture, when I made this tutorial, they did not have this new graphical interface for the quantum experience. It looked like that, the old one. You can do the same thing, just like, I guess they put this down instead of like next to it, but it shouldn't matter. Okay, so what is the problem, or what is the first thing that we're going to try to do? So the first thing is we want to make a circuit, okay, that flips the last qubit of any given state if it was 1, which means I have a state and I want to check if the last qubit is 1, I will flip it to 0. Otherwise, I will do nothing. Okay, that's the whole thing that the circuit is going to do. For example, if I have this example state here, the 1, 0, 1, 1, if I flip the last one, it's going to be 1, 0, 1, 0. Okay, or 10, 10. Actually, like 1, 0, 1, 0. Okay, so how can I do that? First thing, let's think about it. To start with, I'm going to need to make this state, okay, like the state 1, 0, 1, 1 as an example to see if actually my circuit works. So I'm going to start with the quantum circuit simulator first before I actually write it as code. So I have 4 qubits, right? So it's a 4 qubit state, which is 1, 0, 1, 1, right? It's 1, 0, 1, 1. So I'm going to say 1, 0, and then I'm going to add 1, 1. So now I have the state 1, 0, 1, 1. And here it's flipped, but we can ignore that because the way this reads it is the other way around. Okay, so I have like 1, 0, 1, 1. Okay. So here, like I did it here, and yeah. Then I actually, this is the first step. I created this initial state. Now I want to see what can I do to check if the first one, if the first, if this, oh, sorry, if the last qubit is 1. The only thing, okay, I have a question. Yes, the recording will be sent. What are some things that the programming can do that drag and drop simulator can't? Ah, great question. Can I answer it after? I will answer it after Rachel, I promise. Okay, let's first do the circuit and then do the code, and then I'll answer all your questions. Promise. So now I need to check if the last qubit is 1 or not. If so, I want to flip it. So how do I do that? How do I do that? I mean, I'm pretty sure like if it was this classical problem, we'll just say an if else statement. But how would I do that? We can think about it. I will add another qubit here. And you often this qubits that kind of like temporarily variables in classical computing, we call them ancillary qubits. We're just using them to get to a purpose. What is the thing that can actually assure me that the last qubit is 1? If I use the C0 here, if this one is 1, then this one for sure will be 1, right? Because that's how it works. If the control is 1, then it's going to flip the second one, which is already a 0, so it's going to make it a 1. Awesome. But then how can I use this to flip it? Now let me see here. I'm going to go here, and I'm going to go flip it. I mean, apply it backwards, like this. And that's pretty much the circuit. And by the circuit, I mean just those two C0 gates are the one that you can use to flip any last qubits of a state if it's 1. Let's go through it again because I'm pretty sure some of you might be confused. So this is here, I just put an example state, which is 1011. And this here to make sure or to check if this Q3 is 0 or 1. If it's 1, then this Q4 is going to be 1 here. If it's not, it's going to be a 0. Awesome. So if it's 1, what's going to happen? If it's 1, this is going to be 1, and then this one will use it to control and flip the Q3, so it will be 0. If I go here, you're going to see it became 1010. Okay, which is the state that we already that we want, which is 1010. And there is the one here, but we can ignore that one because this is the ancillary qubit, and we do not have to take it into consideration. We can actually just take the parts of the qubits that we want. Now, how do we write that in code? Well, very simple. You basically are just gonna put the gates the way we put them here. So if I go here, and first, I'm going to create a quantum register that has 5 qubits, the 4 that we want, and the ancillary qubits. And I want a classical register, and it's going to be just 4. Why? Why is it 4 and not 5? Because I do not care about the ancillary qubits. It's just something to get me to what I want. But I actually don't care if it's 1 or 0 in the end. So I do not need to measure it, or I do not need to store its value. So I just need to store 4 values, which is the original qubit value. Okay, and then I'm going to create a quantum circuit object and add those 2 registers to it. And then I'm going to just do the X gates to create the 1011 state. And then I'm going to do the 2 C0s. And I'm going to print it, and it's going to look like this. Okay, so look very nice. Let me run this again. Yeah, that looks better because they keep updating it and adding colors to it, so it looks more beautiful. Okay, cool. So now I did it. How do I measure it? Okay, like so far, I do not know what is the state that's going to result is. That's what's called measuring a qubit, which is knowing what the result is. I here have this Qiskit visualization just to plot a histogram. And the way I measure it is we use the measure method. I give the measure method 2 inputs, the quantum register and the classical register, and they have to be of the same size. That's why here I said, hey, just get me the first 4 and the classical register, and then do some measurement. This here, it's just to display this part, but it's not, it doesn't do anything actually except just displaying it. So we're going to skip it now and we're going to talk about shots next. So when I say measure, notice that my circuit, which was like that, now has a bunch of crazy stuff like this. What is this? This is the measurement. So here I'm keep measuring. Like when I say measure, it measures the state at every single time. That's what this means. This means just a measurement operation. Now I can execute it. So here I say execute the circuit or run it. On the quantum simulator, if you're using real device, then we put here the name of the real device, not the quantum simulator. And this shots 1214 is how many times you want it to be repeated. So I told you like the quantum computers are faulty right now and they have a very high noise rate. The thing that they do right now to avoid that or to kind of overcome it is keep repeating the circuit a lot of times and taking the average of a lot of them to kind of increase the accuracy. So that's what the shot is how many times you want me to repeat this quantum circuit in order to increase the accuracy of the result that I'm going to get. Okay, and then I'm going to get the result. So this step, which is measure, execute, result, is very constant, and then get counts. Like you do them in every circuit to kind of measure the last thing. And here, if I said I'm going to get like, again, they have this flip thing in Qiskit, they're still working on it, and it's going to give you the state, but it's going to give it the state backwards. So it's going to give you 1010 or 0101. Okay. So now that's how to run it by code. Now let's go to Rachel's question. Is there something that the quantum simulator can do that the code can? Here's the thing. Quantum simulators are easier than code in some aspects. So this is a quantum simulator. There is another quantum simulator. It's called Quark, and it's built by a Google software engineer. So if I go here, it's kind of the same idea. You drag and drop stuff. Like here, they have like an example circuit. You can just delete it. So you just drag and drop stuff, and it tells you what the end is. In code, like Qiskit itself, or when it first started, now it's bigger and it has more stuff. These gates, like this C0 gate, where is the C0? The C0 gate. See here, we said you can use this as a control and this as a target. But here's the thing. Sometimes you want more control. Like I want 4 qubits as control and 1 as target. And if all the 4 qubits are 1, like 1, 1, 1, 1, then you will flip the target. Now, here is the thing. When you do it on a simulator, you can just say, like, for example, if I went to Quark here, like this is a control, you can say, hey, I want like 4 control, like you can just say control and control, and then a NOT. And awesome, I build a 4 control NOT gate. Great. Can I do that in code just that easily? The answer is no. To do it in code, so here, this is a simulator, but the code needs to translate it to hardware. And the way it does that, you need to see, am I going to need any ancillary qubits? And the answer is yes, you do. How much? That's going to be another thing. Like how do I know how much qubits do I need for every control? Then you're going to have to go do some reading or some studying on how to actually build this circuit in code. So I would say code will give you more power because then you can apply it to a real quantum machine, right? However, simulators are easy and straightforward. You do not have to think about like how actually this is going to be implemented. Like I can add so many stuff. Like this here, the black one means it's conditioned when it's on. So if it's 1, it's going to work. If it's 0, it's not. Then they have this thing, which is actually like if I just throw this away and put this here, this is actually says it works when it's 0. How do I do that in code? You have to build your own function that does that because Qiskit right now does not do that. Does not make control gates that works when it's 0. So in that sense, I would say simulators are better. Or when you're actually when you're starting to build an algorithm and you want to see if it works, I would say try it on a simulator first, because then you only have to care about the concept. Once you have the concept right and you know that your circuit is working and it gives the result that you know it should, Then you can write it in code and go through the struggle of making the code actually work and produce the exact circuit you want. I hope that makes sense, Rachel. Okay. Cool. So we have just 2 questions, and I hope there are any questions. Awesome. So as I said, this is an introduction. In the future, we'll do webinars about more complicated stuff because right now things are simple. And at this level, maybe there is no difference between a code and a simulator because there isn't much complication. But as the circuits get bigger and more complex the gates, then the simulator will give us an advantage than the actual code. So yeah, if you have questions, please drop them because that is it for me. The notebook is on the GitHub. I need to update this picture here and make it one, so I'll do that afterwards so it won't confuse you. But other than that, yeah, that is it for me. I hope you guys enjoyed that, and it was a very light introduction to quantum computing and Qiskit. There is a lot you can do with quantum computer and Qiskit, but that's another topic. Yeah, that is it for me. So I will update the repo, the one in the Woman Who Code, to have more information like this file with the different options you can go with, and the link to the Qiskit documentation, which is very, very great, and it's very beautiful, and it has so much examples if you want to get started. So I totally recommend it. And if you have any question or want to discuss any quantum topics, you can just drop me a message in the Slack channel or email me and I will get right to you. Always happy to talk about quantum. Okay. So, yeah.
Thank you so much, Sarah.
Thank you.
I think Kathy is going to close us out here in just a few seconds.
Hello. So thanks a lot, Sarah, for such an awesome session. I will surely look into quantum computing a bit more because I've been so intrigued after it. So yeah, thanks a lot for that. Also, thank you everyone for joining us today. And you can fill out a feedback form. And once you do that, you can get links to Sarah's notebook and get to know her more, and you can converse with her. So yeah, that's that. So do let us know. And yeah, also do remember to check out our upcoming events. That is transition to computer science programming and tech. So in this event, a great friend of mine, Rushika, is going to tell all of us about how she switched to a non-tech to a tech side. And yeah, really looking forward to it. And also do be a part of our beginner Python study group. So yeah, that's about it. So yeah, thanks a lot for joining us, everyone. And yeah, that's about it. Thanks a lot. Also, if you have any questions, you can just fill out the feedback form and you can get in touch with Sarah.
Yes.
Thanks a lot.
Bye.
Thank you so much, Sarah. This is a really awesome session. Thank you so much. I'll go ahead and end it. Thank you so much, everyone, for attending. I hope you guys come back next time.